For the last lab of Physics 2, called magnetic molasses, we'll be looking at Faraday's law and how a magnetic bar magnet slows down as it falls through a conductor. So we will start off with a little introduction. So the purpose of this lab is to investigate magnetic induction and eddy currents by analyzing how a falling bar magnet interacts with an aluminum tube, and we will compare the observations to computation models. And so in the experiment, it took approximately 1.45 seconds to fall through the tube, and in our computational model, it took 1.059 seconds. And so some fundamental physics principles is we have to use the Biot-Savart law, which relates the magnetic field at a point to a tiny current element, as shown in this equation. We'll have Faraday's law, as I said before, which is when the magnetic flux or magnetic field changes with time, the electromotive force is produced, as shown here. And we will have Newton's second and third law, which states that force equals mass times acceleration, and for every action, there's an equal and opposite reaction. So some initial conditions, we had the bar magnet, the stopwatch, and the aluminum foil tube, as shown in this picture here. And for the system will be the bar magnet and the aluminum tube, and the surroundings will be everything else. And so I'll show you a quick video of the magnet falling through. And you can see it goes slower than it would if you just dropped it normally. Now, the magnet had a mass of 28.8 grams, and the mu of the magnet was 2.3 amps times meter squared. The tube had a length of 46.5 centimeters, a width. Our aluminum width was 0.5 centimeters, the inner radius was 1.5 centimeters, and so the total radius was 2 centimeters. And so we did this, we dropped it through the tube 5 times, and it gave us an average time of 1.45 seconds. So these are some of the data that we collected before we started the computational model. So here's the computational model, and as you can see, we have here where we're calculating the B field, and then we have here we're calculating the flux, and here we have we're calculating ultimately the force on the magnet by using the magnet or the magnetic force of the ring and using the angles. And so that is basically how we found the computational model, and here are our results. So as you can see, this is where this blue part is the magnet falling through, and I don't have a video, but if it were, you'd see it falling through, and it would be 1.059 seconds. And as you can see at first, the magnet is going really fast because it is just falling into the tube. Then it plateaus for a while, so it's going at this constant velocity, and then towards the end, it will speed up again. And so some assumptions we had to make in this lab was 1, the bar magnet acts as a magnetic dipole, and that's why we were able to treat it that way, as we did. 2, that there is negligible air resistance. And 3, that the only forces involved are the magnetic force and the gravitational force. And so some of these assumptions led to some errors, which 1, other electronic/magnetic objects could have skewed the data that we collected, as like the time could have either increased or decreased depending on how it affected it. 2, the friction against the sides of the tube were not considered in the calculations, which could have slowed the magnet down, could have partially been why we got a slower time in real life than we did in the computational model. And lastly, the stopwatch starting and ending may be inconsistent. And so this is just human error. We can't guarantee that it's going to be the same every time. And so that could also be why it was a little slower. So some discussion. So what if the resistivity of the conductor were reduced as close as possible to 0? Well, how would the dynamics of the falling magnet change? So due to Ohm's law, induced current in the aluminum tube would be much greater, hence creating a greater magnetic force on the magnet and could counteract with the gravitational force, preventing it from falling. So this would slow it down further. And another question is what if holes or slats were cut into the tube? How would this affect the ring currents in your model? So induced current in the aluminum tube would be less since the holes would disrupt the current and the magnet would then fall through much quicker. So Thank you so much for listening, and I hope you learned something.